Good afternoon, everyone. I'm Lisa Drusenko, Executive Assistant and Membership Coordinator for the Aluminum Extruders Council and Coordinator for ET16. I'm very pleased to bring to you today a sneak peek at ET16. Our presenters today are none other than ET16 Chairman Craig Werner of Kaiser Aluminum and Chris Jowett of Rio Tinto Aluminium. Craig Werner is currently Vice President, Extrusion Technology for Kaiser Aluminum. And in his role, he applies his extensive knowledge, passion, and leadership to support the company's future growth opportunities. Craig is extremely active within the Aluminum Extruders Council. He is a past chairman. He also chairs AEC's ET16 Seminar Committee and the Business Excellence Steering Committee. After joining Alcan in England, Chris Jowett transferred to what was then the Extrusion of Alcan Canada products. He retired in 2006 from Alcan International in Kingston, Ontario, Canada, after 37 years. Since then, he has been a consultant for Rio Tinto, billet sales in Cleveland, Ohio, and he remains an active member of the AEC Die Committee. He's presented many technical papers, including authoring 13 at ETs, 2 of which won Best Overall Papers at ET 2008 and 2012, and he continues to be a very important contributor to AEC and ET. I just want to let everyone know all computer, audio, and telephone lines are muted. If you have any questions during today's webinar, please select Q&A from your toolbar and type your question in the dialog box. Craig and Chris will be able to address your questions at the end of the presentation if we have enough time, and if not, questions can always be answered in a follow-up email. You can reach out to me, Craig, or Chris directly. And as many of you know, ET is held only once every 4 years, making this a very special event. Not only is it the premier aluminum extrusion event in the world, but this one is currently breaking all past ET records. We have a record number of technical papers, 124, that will be published, and a record number of exhibitors, 123. And with 3 weeks to go, we are closing in on 1,150 attendees. This ET promises to be one you won't want to miss. And team all of that up with the fact that it's being held in downtown Chicago near some of the finest restaurants, shopping, and entertainment in the U.S. We really hope to see all of you there. Remember, this event will not be held again until 2020. Dates are May 3rd through the 6th at the Hyatt Regency Chicago at 151 Wacker Drive. We also have some additional optional workshops on Monday, May 1st and Tuesday, May 2nd. For information, details, and how to register for any or all of these events, please visit aecmeets.org. I'm very excited now to turn the webinar over to Craig and Chris.
Thank you very much, Lisa. Hello, everyone. Today we're going to have the opportunity to talk about 3 different topics. First, we're going to do how ETs have driven improvements in the extrusion industry, and we're going to give you a sneak peek at what the best papers are for ET. We're going to announce them. Second, Chris is going to tell us about his ET paper on what does exit temperature tell us. And the third part of the webinar will be my paper on what matters, pixie dust isn't an extrusion optimization strategy. So let's dive right into it. Just a quick thing on my background. I've been around aluminum extrusion my whole adult life, working for different companies, Alcoa, Werner Extrusion Solutions and Consulting, and now with Kaiser Aluminum. Enjoyed every single one of them. And I've been involved in ETs for over 30 years as well, from the time I started in the industry in 1983 until the present, in all different types of roles. I like this picture because it gives you an idea of the quantity of papers that have been published. And later you'll hear that it's over 1,400 papers will have been published by the time ET 2016 is over. But all of these books from left to right represent all the ETs and the proceedings that went on. There's tremendous value here. There's room for more ETs afterwards, and the next one, as Lisa said, will be in 2020. So ETs are a critical event for disseminating knowledge among our industry and for helping to advance our industry versus alternative materials. We compete with each other, but we also compete with alternative materials. My talk today is going to be a talk about presentations, about other research, about papers, not necessarily about anything in particular other than ET, which is critically important to all of us. ETs help us to drive improvements in the material and alloys, our processes, our equipment, and our overall industrial knowledge base. It assists all of our different customers that we work with by helping us as suppliers to do a better job to our customers. And it also helps our customers to understand why extrusions are powerful design solutions, a little bit about our material and processes, and how to create effective and efficient designs. There's a number of things that come out through ETs and other AEC venues. So the ETs, as we've listed, from 1969 till 2016 now, over 1,400 outstanding technical papers. We were at 1289 as of ET 12. And for me, what's always exciting is to get the ET schedule and just start circling all those papers that we want to go to. And, you know, often there's multiples, there's 5 or 6 tracks happening at the same time, and we have to choose. Got to make some tough choices, but at least you have all the paper presentations to lean on afterwards. We use something called ET time, and it's not a funny thing. It's actually serious. ET time is very, very important because we all rely on being able to go to all these different papers and events. And Bob Werner taught us something about ET time. First of all, he taught us that time marches on. And there's a lot of different people, volunteers and professionals working on at the AEC and on the ET committee. And Bob learned how to drive things through impending events so we could continue to move forward. And this was important because we've got over 120 papers. We've got to go through all the abstracts. People have to author the papers, edit them, produce the presentations, and a lot of work behind the scenes to get this done. And we keep things moving over the 4-year ET cycle. We have a saying, you know, please set your watches to ET time, and that's important because during these sessions we have a number of general sessions and we have a number of overlapping tracks that meet at the same time. So during those tracks we have 20-minute presentations followed by a 5-minute Q&A and a 5-minute chance to change rooms if you want to between the papers. If you don't set your watch carefully, you won't know exactly when to leave or arrive in the next room to make sure that you're not interrupting anybody. So it's very important that we all keep track of the time. And without this, I mean, there would just be no way to have a smoothly running conference. So we'll remind you of that at the beginning of ET. The other alternative meeting of ET time is, you know, the ET committee works through, first we start with a committee recap of the last ET. We send out a call for abstracts. We work with the authors on their papers and presentations. And then finally we hit the big event, number 5. At the same time, you've got companies and universities on their own time schedule, working through their project concepts, technical development, and finally completing their papers and presentations. ET is the sole event worldwide and the most important event worldwide that focuses exclusively on the materials, equipment, processes, and other things related just to the aluminum extrusion process. The presenters that we use have been vetted to give us some really excellent work and value to all of our attendees. ET is a worldwide offering, and we bring the best research, technical, managerial, and other concepts from around the globe. And all of those people who are also from all around the globe come not only to benefit from the presentations and actively participate, but they get to share knowledge and they get to network with other people. And there's simply nowhere else on earth you can go to see so many aluminum extrusion people working together, sharing information and networking, just on the topic of aluminum extrusion. So when we look at ET, it's made up of a number of things. We have the team that's set up, we have the abstracts, the published papers, the presentations, the venue where it's taking place. We have the ET Expo, which is the exhibition hall. Alyssa said we have 120 different exhibitors. We have the showcase where we see examples of different extrusions and how they're used. And probably most important, we have the networking opportunities to meet with your peers from all over the world. Little bit of history of ET. It started in 1969 with a simple meeting in New Orleans. It was chaired by Maurice Roberts, who pulled it together. And handouts were given in 3-ring binders, and everything was presented on overhead projectors. The next 2 ETs were held in Atlanta in 1977 and 84, and at that time we started to bring in tabletop displays, more bound proceedings, and networking. And the next 4 ETs were held in Chicago, where we added the large exhibition hall, and by now everybody was planning on these 4-year cycles. We went on to not only electronic but also printed proceedings. So the electronic gave us the ability to store them all on our computers. In the next 2 ETs, 04 and 08, were held in Orlando. ET Showcase was added here. ET 12 was in Miami. And ET 16 is in Chicago, back again to Chicago. High-level view, I mean, when these ET papers are written, whether it's by a company or university, the concept has to be conceived of and approved. You've got to schedule all the work that's going to be done, all the studying and resources, lab time, production time. You have to develop the hypotheses that come out of the studies, run some experiments to test the hypotheses, adapt plans depending on how the results were going. You might have to make some changes, and then finally draw conclusions, but you're not done then because you have to draft the paper, submit it for approval, get the final technical paper sent in to ET and approved, and then finally the presentation needs to happen. So these authors and the presenters and all of the technical people behind them that support them, tremendous amount of work goes into preparing for ET, and we thank them for all of their contributions to our industry. I'm not going to go through this slide in detail, but it was from a light middle age article I published years ago, and it actually shows the evolution of the tracks over the years, which is interesting. We've kind of settled on our more traditional tracks in ET8 and 12, even ET4. But looking back in '69, there were no tracks at all. It was just a bunch of papers, and the tracks allowed us to begin to organize things and collect papers under different categories and also advertise for the need for papers in these categories. So the tracks we have for ET16 are billet process and equipment, extrusion and die practical, extrusion and die theoretical, extrusion equipment, value-added processes, and management issues. Those are our 6 tracks. At ET, we have companies and universities working together, and I used the word co-opetition I found somewhere. But we have researchers and authors working together. Sometimes they're working alone, sometimes together. And they're not competing, but they're sharing to improve our industry. Because while we compete, and it's in red here, the true competition is the alternative technical solutions and materials that are available besides aluminum extrusion. We want to make sure that extrusions are used in the designs and the application where they're the best solution. So at ET, we'll have some best of conference and best of track papers. We'll have the Maurice Roberts Award of Excellence. And this is just a picture of some of the winners from one of the best of conference and best of track photos. This ET, we're going to have papers that cover alloy and process controls to help us make better products for key industries like automotive. It's going to cover some casting technology information where we'll learn about billet quality, extrusion process, and the resultant product enhancements. There'll be some aids to product designers and extruders to really understand our total value stream and how to optimize it. There's some novel extrusion equipment technologies that will be set forth and explained and demonstrated. Some, as always, key design and maintenance approaches to improve quality and cost in our operations. Some alternative approaches to finishing for enhanced performance and environmental impacts. Key safety concepts are also always discussed at ET. It's a critical thing that we cover. And we'll all learn some more about some of the key extrusion variables and how we can use these things to best optimize our productivity, quality, and costs. So the best paper of ET16 is Extrusions for Automotive Crash Applications from Rio Tinto. Congratulate them on that. And now we're going to go into the best of the 6 tracks. The best of Extrusion Die Practical is the advanced aluminum alloys used in the manufacture of products in the extrusion process. Best of Extrusion and Die Theoretical is modeling the effect of manganese on extrudability, mechanical properties, and grain structure of 6082 alloys. Best of Management is a novel methodology for optimization of properties, cost, and sustainability of aluminum extrusions. Best of Billet Process and Equipment is innovations in billet casting and homogenization. Best of Extrusion Equipment is the Hybrex, an innovative extrusion press with hybrid drive technology. and the best of the value added will be a surface topography of aluminum extrusions after caustic and acid etching and its implication for defects. One thing a little different at this ET is that all these best of papers won't be competing with some of the other papers. So when you see the schedule and review it in detail as you map out your plan, you'll find that you have the opportunity to see, everyone will see the best of ET paper on the top, but out of the 6 below, you'll get to see 3 out of the 6 of those. There'll only be 2 of them competing with each other at any given time, which is a change to our process. The team that makes up ET is the upper level team, myself and Jim Sanderson and Bob Peacock, both past ET chairs. A lot of experience there. And then there's a committee of over 30 people that work with the authors and work with the staff to really deliver an outstanding conference for all of us. And speaking of outstanding support, we get that from the AEC staff. We just have some terrific people that keep this process moving through the 4-year cycle and make it all look easy when we show up at ET. There's a lot of other extrusion professionals who don't show in this picture because they're the people supporting the authors and supporting the committees and maybe editing some papers for their companies and things like that. But there's a lot of people that go into making this ET a success. So the chair, as I said, the ET team as it exists now for 16 is this group. And then we have some track chairs, David Asher, Chip Edwards, Jerome Foreman, Olivier Gabus, Frank Kraft, and Bill Rogers. Those are our 6 track chairs. And then we have a large number of committee members, which I'm not going to read through all of them, but they're listed here. This is a picture of the ET team from the past. And I'm overlaying with this because I really wish I could have a group photograph of all of the researchers, technicians, authors, presenters, and all the other people who provide the support. Unfortunately, I don't think we could all be in one place at one time, nor do I think we could get all of us to fit in a picture where you could recognize any of us. There'd be so many people in the photo. ET is a chance to build our industry together, providing ever better materials, processes, and equipments. Don't miss out on your chance to be there. And this little quick slideshow is just showing my ET books on my countertop in my office, adding up one ET after another until finally we get to ET 12. And I'll be proud to get another picture with ET 16 just to the right of that between our die. So that these books that you see, these represent over 40 years of people in our industry working together to share and develop the high level of understanding we have in our processes, materials, equipment, etc., that without working together we would never achieve. So thank you to everyone from the past and the future that's helping to make our industry successful. We will see you all at ET 2016 in a few weeks in Chicago. Should be a great opportunity to get together, network, and learn. I'm now going to turn the presentation over to Chris Jowett. And Chris, you should have control.
Thank you, Craig. Good afternoon, everybody. As part of this sneak preview, I'd like to give a very brief summary of our ET paper on extrusion temperature. I see on the schedule, I'm very glad to say, we are first on after the introductory general session, and it's followed by Henry Velberg from Norway talking on a similar subject. After that, we can relax for the rest of the conference. Basically, today, I'm really here just to give Craig a break between his two sessions. We all talk about how important temperature is, but I don't believe we take it really too seriously in practice. We talk about the 3 rules of extrusion being temperature, 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 but in practice, we don't measure much. We measure 2 basic temperatures. We measure billet temperature. We measure exit temperature. We don't really measure a lot between there. We control die temperature, we control container temperature, but we don't really measure temperature rise in the container, what's happening in the die as we extrude. Although it's quite easy to do so in the lab, it's not something we can do easily in production. So back to the title. I'm not sure it's a great idea to use a title as a question, as it usually requires an answer. But off the top of my head, the answer to this question would be, it really doesn't tell us a great deal. It tells us we've exceeded the solvers, and we're going to get magnesium silicide in solution. We're going to get properties. But apart from that, really, it doesn't tell us too much. However, when you think about it, there is another benefit. It can help in achieving consistency. It tells us if we're running at a certain exit temperature as measured by the pyrometer, then it tells us we're running the same as yesterday. We can produce consistency. But this is only useful when you say, for example, for die 1234, exit of 1050 Fahrenheit is perfect, and then we can run that every day and get good consistent material, consistent performance. Exit temperature tells us nothing about what's happening at the bearing, what's happening in the container as the metal flows through, which really is the thing which determines finish and die wear. One thing we do know is that exit temperature is hot. This is a lovely kind of almost a surrealistic picture with an infrared pyrometer, which shows us, you can see that shadow of the pyrometer above the exit of the press, but you can see how hot things are in the die as the extrusion leaves the press. We know we can reach through measurements, and this has been reported in ET before, we know from experience that we can reach temperatures as high as 630 Celsius, which is the alloy solidus, the melting point of the alloy. We know we can reach these temperatures, which is 1170 Fahrenheit. And we can draw back dies, which are heat treated at 1100 Fahrenheit. But this just illustrates one thing you can look at. This is measuring bearing temperature, the temperature of the bearing at the exit of the press, and we're also measuring the red plot shows the optical pyrometer reading. It shows us really that what we measure at the exit of the press is substantially colder than what's happening at the bearing. And really what we wanted to do with this paper was to try and relate these two, find what are the rules which relate measurements at the optical pyrometer with what is happening at the die bearing, which allows us, and if we could calculate using optical pyrometer values, if we can calculate what the bearing temperature is, we're getting so much closer to maximizing productivity and maximizing speed. This is some data we recorded a long time ago. This was a bit back in British Alcan Extrusions days. What we did here was run a series of dies at maximum speed. Maximum speed we determined as being the beginning of speed cracks, surface melting, a bright surface, which is about 1160 Fahrenheit, 630 Celsius. And we found that the measurements of the optical pyrometer at this point was substantially lower than the bearing temperature. Yes, we know that. However, it did seem to vary with profile thickness. It's an interesting observation. For example, if we want to run a profile which is, say, 60 thou wall, 1.5 millimeter, we want to run it as fast as we can, we should really be looking at a profilometer as a pyrometer value of about 1075. If we run a profile which is 5 or 6 millimeters thick, we really can't go much above 1015 Fahrenheit because we're going to produce a melted surface. This tells us that there is some interesting relationships. So what we decided to do for this paper, we can't measure this stuff on a production basis, so what we really need to do is model it. So we used a commercial finite element package, Deform 2D, in fact Deform 3D. We use TD for this for simplicity, and a very neat tracking tool. So initially, before we could do any modeling, we have to validate this model. So we did a lot of experimental data. This is a picture of, and I'll just show you the kind of data we got. This is our experimental press, which we run in Arvida in Quebec, with Nick Parson there at the controls. First things we measured, container temperature. We have on this press we have thermocouples located at the liner wall. We can measure accurately the temperature of the billet as it extrudes. And the kind of data we got was this. This shows the liner thermocouple varying on a 16 billet run, 4 billets to preheat, 4 billets at low speed, 4 billets at medium speed, and 4 at high speed. And it shows the cycling. It shows us that the thermocouple located near the die end of the container, the temperature rise is something like from 450 to 490, 40 degrees Celsius. This data we can use and see how the model can predict this sort of information. The second thing we did was to run this die. This die we used for these tests was a simple half-inch bar. We filled the die with thermocouples and measured temperature, and this is some of the data we got, again with this 16-billet run. If you look at the right-hand side when we're running at high speed, the temperature at the bearing varies between 440 up to 600. So with this data, which we could test our model, and this is the model we used. As I say, it was deformed 2D in this case. The upper figure shows the model, the bottom figure shows the mesh, which allowed us, and I'll just give an illustration of the kind of information we got from this modeling. We used a point tracking method, which is a rather neat way of measuring and predicting what the temperature is through the thickness of the profile and throughout the container. On the plot you'll see numbers, that is time. And you can see the metal is the red metal, for example, on the outside, the red flow path, which is the material going to the bearing. It runs a lot slower than it does through the center. This is in seconds. And this is the kind of information you get. This shows the temperature with time for the center of this bar and the surface of the bar, and you can see the red plot above is the hottest. The bearing is running a lot hotter than the core of the aperture, the core of the die. You can see, for example, that the surface temperature in this case is 580 Celsius, whereas the metal running through the center of this bar is 520, substantially cooler. And we have the plots at various positions across through the thickness of the profile. What is really interesting with this is how fast the temperature drops between the surface and the core, and the material becomes more uniform temperature. It drops to 560 Celsius, and this occurs within about 0.1 of a second. And I'll just show you a couple of illustrations of extremes. This shows the flow of metal through the die at low speed. Surface temperature something like 580. In this case, we're showing at low speed the temperature drops from the surface of about 1050 Fahrenheit, drops to about 1000 very rapidly. In this case, it's 0.2 seconds between the maximum and by the time it reaches uniform temperature. So this gradient has vanished very fast. If you look at what happens at high speed, in this case we're running with an extrusion surface temperature of 640 Celsius. It's above melting, but it still comes out as a solid profile. In the middle of this bar it's 540. It's 100 degrees or so different, but this temperature gradient vanishes within 0.2 of a second. We often think, we know that we believe that dies run hot, and we measure, by the time we measure them, it's cold, and we think it's something to do with cooling. It's not. It's purely due to conduction within the profile, and within 0.2 of a second we have a uniform temperature. And I'll just show you this plot. Maybe it's not that clear, but it shows the upper curve here is showing what the metal flowing across the bearing. It rises up to a temperature of 1020 Fahrenheit, cools within 0.2 of a second to 945 Fahrenheit. By the time we measure it at the press exit, it's 930. So the cooling is only 15 degrees, but the actual conduction and the reduction of this gradient is in a matter of 0.2 of a second, and it's well under 100 degrees. It's well over 100 degrees C. And I'll just show you a couple of illustrations of the kind of thing we can model. This is 5% of this material extruded. This is 30%, 80%. You can see that the temperature is extremely local. The material, which after leaving the die, the temperature is uniform within a fraction of a second, long before the metal's left the bolster. We're never going to be able to measure this. That's why we think that's why modeling is so useful. just to give you a couple of other illustrations, what can we predict? This shows the surface temperature in the bearing. It's a 15mm bearing for this profile. And you can see that the temperature is hotter, obviously hotter as you extrude faster. The maximum temperature is in the middle of the bearing. This is the profile. If we look at the other data, which was the temperature of the die, it gives a very different picture. It tells us that the temperature of the die, again, is a lot hotter at high speed, but the temperature is highest at the entrance of the bearing, and it drops throughout the length. This maybe is not expected, but it certainly does tell us why dies wear at the entrance part. They tend to start washing out at the entrance part of the bearing, not at the very entrance, but near the front of the bearing. And it tells us there is a difference between die temperature and extrusion temperature. And this illustrates it and demonstrates the difference. It shows that all the heat is being generated, and you say, why is this so hot at the entrance and not the back, considering there is continuous shear on the bearing surface? It's mainly because the die is not uniform, and the back of the die, the exit side of the die, is colder than the die face. We have a perpetual supply of hot metal coming in, adding heat. And obviously, it explains if we're running extrusions at 630 Celsius, we could certainly run, the dies are probably running at 640, 650, which is well above the tempering temperature of the steel. No wonder dies wear out. And this shows the gradient. The blue line on the left-hand side shows the gradient across the diameter. So, some conclusions. This is a very brief summary of the paper. We've basically developed a model which gives us very accurate allowed temperatures, and it can predict temperatures in the liner, in the container, those which our data supports. The temperature of the die bearing, which basically controls the surface finish, is significantly higher than that given by prod thermocouples, an optical parameter. We knew this. But at maximum speed, there is a trend for the exit temperature measured at the press platen to be higher when the profile is thinner. This is new, and this says if we want to somehow predict what's happening at the bearing using an optical pyrometer, we have to accept the fact that it varies with profile. So once we have established the rules between profile temperature at the exit of the press, dimensions of the profile, we should be able to predict what's happening at the bearing, and we can run more at temperatures which are not too hot for giving poor surface and not too hot for destroying bearings. The steel bearing is hotter than the extrusion in most situations. This is surprising. At high speed, the aluminum temperature in the bearing is often more than the melting point. Yes, we have measured 660, 670 Celsius, which is well above the alloy solidus, the melting point, but the profile does still come out as solid because the conduction, it freezes so fast. The surface layers of the bearing are regularly above steel tempering temperature, yes. And one last couple of conclusions. We believe it should be possible to estimate die bearing temperature knowing optical pyrometer output and profile dimensions. This is something maybe we can work with optical pyrometer manufacturers to see if there's a way in which we can calculate the exact bearing temperature just with an optical pyrometer. And there's an exciting possibility. We talk about isothermal extrusion. Isothermal what? At the moment, all we're measuring with isothermal, trying to get isothermal extrusion, is isothermal exit temperature, which really isn't that useful. What's far more useful will be to have to be able to develop a process which gives us isothermal bearing temperature. And at that point, I will finish, and I'll pass you back to Craig.
Well, thank you, Chris. You certainly whetted my appetite. I'll be sitting in on your talk to hear the other points that you didn't have time to go over with us and reading through the paper, so thank you. You noted that there are three key variables, temperature, temperature, and temperature, but actually, depending on who you're talking to and what the topic is in extrusion, other variables or other key points are safety, quality, and productivity. Those are three that pop to mind. And in my world, with the optimization work I've done and reported at ETs, it's really data, data, and data, and data integrity. So I am going to take us through my presentation. And this one is called What Matters? Pixie Dust is an Extrusion Optimization Strategy. And this is an interesting synthesis of a couple of different approaches that I'm going to show you. So bear with me as I take you through it. First of all, of course, extrusion is a competitive material internally with our competitors in the extrusion industry, but also with other materials. What I love about the process and the material is it can be pretty well defined mathematically, and there's been a bunch of papers on extrusion optimization written about this. We have some good data, which AEC collects for its members. It's called the Annual Benchmarking Report, and I'll show you some pictures of that. And my ET paper, ET12 paper on equipment optimization, I delved into that same analysis and kind of tied it in with the AEC's annual benchmarking reports to develop what I'm going to show you in this paper. So we're going to combine these two approaches. First, we have the Key Indicator Survey Report. This is the annual benchmarking report that comes out from the AEC. This is the 2014 cover. In it, there's a great deal of information. I've only copied a couple slides to show you, but we have information on the number of presses that are discussed and that are analyzed, as well as the number of pounds, percentage of metal utilized, pounds per hour, that sort of stuff. There's also information which breaks these presses down into different percentiles. So 90th percentile response will refer to those presses which are at the 90th percent of performance. So we can look at typical extrusion presses and also 90th percentile extrusion presses. And then there's more information where you can dig into even more information, 25th typical, 75th, and 90th percentile. There's a number of pages and a lot of data in this report, but these are the things that I focused on. So, looking back to my ET12 paper, I'm going to give just a couple minutes of an overview on that. Equipment's often purchased based on gut feel or by focusing on just a single area of concern, but actually by using a systematic modeling-driven approach, you can look at different equipment variables and the types of profiles you might run on it and model exactly what's going to happen. So you detail out the equipment parameters, you look at some profiles to model, and then you use the actual model results to forecast the productivity and recovery, and therefore the total annual dollars that will be spent for the mix of product that you're looking at. So it's a powerful way to get some information. I encourage you to go back and read some of my earlier ET papers if you're interested. But the results show up in a couple of columns in those papers, but there's a lot of work going on in the background to calculate what's happening. Ultimately, you can take a look at this and you can see this is a chart, for example, that shows for a particular mix of business as the runout length changes on the x-axis and as the billet length chosen for the container, Chris, I think you're moving my mouse around, as that changes on the different colors of the lines, you can see what the total conversion cost is on the left. So it helps you to see how to match up runout table length, billet table length, and also this was done with many different pounds per hour of log furnace, so we had different charts showing this. So once you model it, you can get a lot of great information. So what really matters? I mean, to me, what matters is, first, we have to eliminate and control every possible cause of variation in our process. That's the way we get better control over things. Once everything's running smoothly, we can focus on safety, quality, delivery, productivity, and cost. But, particularly when the equipment isn't running well, when there's a lot of downtime, when there's a lot of interruptions, it's hard to get any of those things performing properly because of abnormal conditions that pop up. So at a high level, that's what matters. But that's not what I'm going to talk about here. I'm going to talk about looking at the AEC Key Indicators Report and looking at 8 and 9 inch billets. This was listed as 8, but less than 10, so that would typically be 8 and 9 inch billets. I just used as an approximation technique 95% of the pounds per hour for the typical extruder, and the 90% extruder were used as an approximation of what an 8 inch press would achieve. It's not 100%, it's something less than that. I'm not sure what the number would be, but I just used an 8 inch press to model all of this. From that point, once I decided that, the classifications are for a typical extruder, it turned out to be 2,272 pounds an hour, and for a 90th percentile extruder, 3,000 pounds an hour, 3,043. And there's also a difference in the yield and the recovery, 79.5% for a typical extruder and about 85.8% for a 90th percentile extruder. So the reason I was trying to focus on these is I was trying to figure out some way to pull the data together in a way that would be useful to extruders to understand what makes a difference. So I used Werner data that we had developed and used over many, many years for many, many different what-if situations. That's where I learned all of these techniques and developed them. That data was all changed. I changed all of the profile numbers. I changed all of the weight per foot. I changed the extrusion velocities, but I at least used it to represent a mix of product. And then I took that mix of product, and in order to get the Werner numbers in terms of pounds per hour and yield at the typical, I had to hobble it quite a bit. I had to slow down the velocity. We were always known as a very fast extruder, cold and fast. But I hobbled the velocity and I added a little bit of scrap in order to achieve the typical extrusion, 2,272 pounds per hour and 20.5% scrap. I did this modeling what I felt might be a typical 8-inch press, 30-inch maximum billet. Billets cut to 2-inch increments, stopping extrusion when the butt size is reached, and some other characteristics that are listed there. And I then ran it through all the different shapes that we run, and I said, hey, what would it cost to run this book of business across this typical press? And it turned out to be 3.5 million pounds or dollars a year. That was for 6,000 hours of scheduled extrusion, basically, 5 days a week, 250 days a year. And out of that, we would generate just over 3 million pounds of scrap. I had a scrap valuation of about 18 cents per pound to send it out, get it processed, and get it back as log. And that was $3.5 million to do it on a typical press. So then I looked at a 90% extruder, and I came up with what a 90% extruder would be in order to reach the same number of dollars, the $2,500,000, and the pounds per hour listing that we had. So I detailed this out. But what's interesting is kind of how it all compares. So if I look at the first line on this chart, typical 8-inch press, it was 2,272 pounds an hour, where the 90th percentile extruder was at 3,043 pounds per hour, and the scrap next to it. But if you continue to look over to the right, you'll see when run through my model, it shows that we're going to save 1,645 hours of production time because of the higher pounds per hour and the lower scrap rate. That'll save us over $800,000 in costs. If you look at the $3 million versus the $2,177,000, scrap costs will be another couple $100,000 worth of savings, or a total savings. Looking at if a typical extruder was extruding the book of business, or if it was run on a 90th percentile press, a total difference of about $1 million in cost. Now, besides that $1 million in cost, you have that 1,645 hours, which if they were run at 3,043 pounds an hour of the 90th percentile extruder, that would give you additional pounds, and I just put in 25 cents a pound of profit just for a what if. That's another $1.2 million worth of value if the press was sold out. So you're somewhere between, looking at the far right column, somewhere between $1 million savings and $2.2 million savings if you could make a typical press into a 90th percentile press. So the question is, how do you do that? Well, I tried to use the model to show different ways that we might do that. When I run these models, I typically run a case, and each one of these columns represents a different case. So in the first columns, these are where I do my calculations, and this is what a typical extruder would be. So just to the right of the dark line is the locked in as a typical extruder. And then I run a bunch of different cases, and you'll see the details for this later, so don't try to stare at the tiny numbers. I'm just giving you the flow of thought process. I run a whole bunch of different analyses. Here would be a 90th percentile extruder. And actually, if you look down, you can see the numbers I was talking about, the $1 million here and the extra productivity or the extra sales you could have for a total of somewhere between $1 million and $2.2 million savings. So I run through all these different what-if cases, and the length of the arrow is just trying to show what the benefit of each of these is, and I probably thought you might want to see more about that, so that's what I delved into next. So finally I ended up and I said, well, we can do all of these things, but to get from a typical to a 90th percentile extruder, there's going to have to be a lot of investment in equipment probably. So then I asked myself the question, what if I just did partial improvements and I layered on a bunch of partial improvements? And you can see I can get halfway there. I can get, instead of the $2.2 million savings, I can get to about $1.2 million savings just with a bunch of partial improvements. Now this is on a book of business that I used as representative for my analysis, and it's based on particular presses and particular profiles that it was modeled on. But I'm going to show you exactly how that sugared out. So the base case was an improvement of 0, the 90th percentile extruder 2.2 million, and finally the typical extrusion with some partial improvements up to 1.2 million of that $2.2 million conversion cost savings. So here's the listing of all the different cases, and I'm going to go through these in a little bit more detail, but not through every single one of them. But each one of those columns in that spreadsheet, I've just summarized what was done. So if we look at the first two cases, we have the base case and the 90th percent extrusion, but then what if instead of buying it in 2-inch increments, we bought it in 1-inch increments? Well, our pounds per hour goes up ever so slightly, our scrap goes down a little bit, our cost goes down, so you end up somewhere between the difference in costs here, $100,000 and another $50,000. So you could be somewhere between $100,000 and $150,000. And I did that for all of these different analyses. So here it is. If we used a log shear or a hot saw, we could see a benefit of about $280,000 if we were able to sell out the business on the press. If we put a larger log furnace on, because in this case it was modeled with a constraint to the log furnace, a little bit smaller than maybe this press should have had, that would have been a very big savings of $450,000. But that's, of course, only true if the press you're modeling actually has a smaller than required log furnace, or if it isn't tuned up properly. And here's a case where we increased the cooling table from 145 to 165 foot, and we increased the possible billet length from 30 to 32 inches, and that's worth a couple $100,000. So now let's walk through some of the details. When I look at what I had to do to call partial improvements to get me to that $1.2 million savings, we went from a 30 to a 30.5 inch billet. So, maybe we can squeeze out a little bit longer container liner or just trim a little bit. Use billets in 1-inch versus 2-inch increments. So you don't have to necessarily put a log shear in, just particularly for the high volume shapes, make sure you're buying them to a 1-inch increment. Increase the log furnace capacity. In this case, I had a low one of 3,100 pounds an hour, but tune it up to maybe 3,500, just making sure that everything is working properly. Focus on dead cycle. Take a second out of dead cycle. Change your die change time from about 150 seconds to 90. Figure out a way to put another 10 foot on your cooling table. Evaluate your scrap and see whether it's possible to cut 1 foot less scrap per run out. Maybe by making sure that you've properly etched samples to know whether or not you're getting into coring and other problems, and taking the minimum scrap that's required for each particular shape. And finally, increasing the extrusion velocity by about 5% and the system utilization by 1%. So the uptime by 1%. So I just wanted to see what would be the effect of layering each of these things in, and it was over half of the value was there. So while it's good to buy new equipment and put all these things in, just focusing on a number of different things can make the improvements that we'd all like to see in our operations. And this is just an example of some modeling work that was done. It doesn't represent any particular reality, but it is indicative of what can happen by focusing on all the different details that define our processes and our costs. So in here, and you'll see it more in the actual ET paper, I have all of the different things that I tried, and I have an explanation of what happened as a result of this. When you read the paper, all of this is documented in there. So it tells, by going from a 2-inch to a 1-inch billet, what happens and why that it happens. So for each of the things that I looked at, it shows the amount of money in red there and also why it happened. So I'm not going to take the time now to go through each of these. But I will say that, for the model that I created, It is possible to get there by doing the things I talked about previously. I listed those out earlier. All these small changes add up, and that's probably the biggest one there. The cooling table increase from 145 to 155. That may take a little doing. But when you model it, you'll know the exact effect of that one particular thing if the rest of the things are held constant. So the point of the thing is, there isn't any pixie dust. There's no magic way to improve. We have to improve by focusing on the details of our processes, of our equipment, of our material usage in ways that we can combine a whole bunch of small improvements to one really big improvement. So all of these various details matter. And how do you do that? How do you move from a typical to a 90th percentile, or even what Paul Robbins would call the super extruder in his article? First of all, you got to focus on what matters in your own operations. Second, there's a lot of help you can get from your suppliers, your equipment suppliers, your metal suppliers. They have a lot of knowledge. And third, those members of the AEC have the opportunities to participate in process optimization workshops, extrusion excellence course, die clinics, press maintenance workshops, a bunch of online webinars that we've done for years now, many, many in-person offerings, and finally, of course, ET, taking the full circle back to ET 2016. When you take advantage of all these learning opportunities, it can make a difference. So that is the end of my slideshow, and I'm going to turn it back over to Lissa in a moment. But first, I hope to see all of you at ET 2016 and have a chance to network with you, and we look forward to seeing you there at what will be a great event. Over to you, Liz.
Thank you, Craig, so much, and Chris, for giving us a sneak peek into ET 16. You'll see complete presentations of both of these papers and many, many more, along with the best papers and the overall best paper. So it's going to be a really, really exciting event. So far, we don't have any questions, but please don't be shy. If anyone has any questions, please type it into your dialog box. Again, for more details on how to register for this wonderful event coming up in May, visit aecmeets.org to register. If you have not registered, or you have registered and you haven't gotten your hotel rooms yet, they are booking up quickly, and we're worried that we're going to run out of rooms. So by all means, make sure you contact the Hyatt directly, and you can get the Hyatt's information as well through aecmeets.org. The end of this month, we have another really, really good webinar in the finishing category scheduled, and that will be on April 27th at 1:30 Central Time, when Scott Moffett of PPG will present architectural applications for liquid and powder fluoropolymer coatings, an objective review, CX004. Still have no questions. Those were both really, really great presentations, and we really appreciate the two of you sharing those with us today.
Can I ask Craig a question?
Of course.
Sure.
I was interested. I'm sorry I used my mouse. I was so interested in it. I was like to zoom in on it and try and get stuff, but I lost. The question was, what about the impact of dies which don't run? Is there it's a big impact if 10% of your dies only produce 2 billets worth of scrap, and then you have to pull the die.
Yeah, actually, I did not build that into my modeling. It could be built in with, some percentage of what percentage will not run and how much, what the die change difference might be from a planned die change to an unplanned die change, where you need a few extra seconds or minutes in order to, get to stop and change the dies when you don't have something prepared, like on a NASCAR race. Unfortunately you had a flat all of a sudden. You got to go find the spare tire to put on. We got to put the new die in. So I did not model that. But it could be built into the model. It just wasn't done.
Okay. It could be a big one. That's what I'm thinking.
Oh, absolutely. For me, that usually goes into the utilization effect and the scrap as well, and the recovery. Yes. All right, listen, Chris, I think, and to all the attendees, thank you for your attention. I think I'm not seeing any questions, other questions popping up.
No questions have come in. I think most everybody knows how to get a hold of us, though, so if anyone thinks of anything afterwards, you can always reach out to any of the three of us or reach out to me, and I'll forward the questions to the appropriate party. I'd like to thank everyone for attending today, and we hope to see you the first week of May in Chicago. Thanks, everyone. Goodbye.